the X-ray beam, right? So any area on the film that appears white, that means that the X-ray beam did not hit the film, right, at that particular area, right? Now, if an area appears black, on the other hand, that means that there was nothing in the way of the X-ray and it basically strike that part of the film, right? Now, if they are gray, well, there will be, right, areas varying degrees of gray. That means different degrees of the X-ray beam basically was stopped, right? So it basically was dependent on the density of the object, right? So it wasn't, a lot of it wasn't, it didn't make contact with the film, all right, as compared to the areas that are black. You guys understand what I'm saying? Any questions so far?
Doc, when you said the X-ray beam is stopped, does it mean the beam is rebounded or the beam is
It is
absorbed by the fluid?
observed, yes, it is
Right.
observed by the dental tissue, right?
Good.
However, it can be deflected, right? It can also be deflected, which we will look at as we go along, right? So the final shadow density of any object is thus affected by the specific type of material of which the object is made. So for example, if a patient has an amalgam filling in their mouth, right? And obviously this will be within the dental, the teeth, within the teeth, right? So it's surrounded by enamel, dentin, and the pulp, right? You will see the difference between the amalgam, because amalgam is metal, right? That means it's denser than normal tissue within the body. So that will completely stop the x-rays. That area will appear white on the film, right? Compared to the enamel, it wouldn't appear as white as the amalgam filling. All right. So it depends on the thickness of or density of the material, the shape of the object, the intensity of the X-ray beam used, the position of the object in relation to the X-ray beam and film, and the sensitivity of the film. And all of these points, we will go through them as we go through the presentations. All right. So you have a better understanding of what we're talking about. So 3D anatomical tissues. So the shape, density, and thickness of the patient's tissues, principally the hard tissues, it must also affect the radiographic image. So therefore, when viewing the 2D radiographic images, the 3D or the three-dimensional anatomy, responsible for the image must be considered. So again, you need to have a sound anatomical knowledge for the interpretation of your radiographic images. Right? So here we have another one basically showing us or identifying some of the basic anatomies that we should know, and we will go through these as we go along, right? So we know there's the periodontal ligament space, right, which is between the bone and the tooth, right? So as you can see, let's see. So as you can see along between the bone and the tooth, you can see a dark line. You guys can see that? A dark line that runs along the roots of the tooth or the teeth there, right? We can identify that as the periodontal ligament space, right? And all of these anatomy we will go through as we go along the course. All right, we have the lamina dura, we have the trabecular pattern of the bone, right? All of these things we can identify. So superimposition and assessing the location and shape of structures within an object. So the shadows they cast Shadows cast by different parts of an object or patient are superimposed upon one another on the final radiograph, and the image therefore provides limited or even misleading information as to where a particular internal structure lies or to its shape. All right, so this again, you need to know your anatomy so you don't be misled. All right. So there are limitations imposed by a 2D image and superimposition. And the two main limitations are that, again, you need to appreciate the overall shape of the object, right? You need to understand it and appreciate the shape, right? Because obviously, again, it will be superimposed on other structures, right? So also there's superimposition and assessing the location and shape of structures within an object. That is another limitation, right? So sometimes the mental foramen that is between the mandibular premolars, a lot of times persons tend to misdiagnose that as some sort of dental disease, not taking into consideration that, you know, that is an anatomical structure. All right, so you need to be very aware of where your foramens are. All right. So the quality of the radiographic image. So the overall image quality and the amount of details shown, it depends on several factors. We have first the contrast, and this is the visual difference between the various black, white, and gray shadows. We have the image geometry. Now, this is the relative positions of the film, object, and X-ray tube head. So as we said, there are different techniques involved in retaking the images. So if it's not in the correct position, we can have some errors occurring, such as elongation of your image. So it looks too long, right? It can look too short. We call it foreshortening. All right. We can have blurred images due to movement, or we can have other things also occurring, which other errors, there's a lot, which will be occurring if you make certain errors. And obviously you need to know which error was made so that you can, you know, do the right thing afterwards. Now, the third is the characteristics of the X-ray beam. And then we have image sharpness and resolution. So these are the factors that are dependent on the several variables relating to the density of the object, the image receptor, and the X-ray equipment. So positioning of the film, object, and X-ray beam. So the position, the position of the X-ray beam, the object, and the film. And when we say the object, we're basically referring to the teeth or the structure within the mouth that we're taking the image of, right? We need basic geometrical requirements, and these include the object and film. They should be in contact or as close as possible to each other. The object and the film, they should be parallel to each other, and this mainly applies to some techniques, not all of them. All right, because we have the bisecting technique, and this the film and the tooth in question, they're not parallel to each other. All right. We have the X-ray tube head. It should be positioned so that the beam meets both the object and the film at right angles. And all of these factors help us to position these three elements so that we can get the best diagnostic image. All right. So this image is basically showing us how we place the film in relation to the tooth when we're using the paralleling technique. All right. And the rays, the X-rays basically are parallel to the tooth and the film. All right. That's why it's called paralleling technique. Now the X-ray beam characteristics. So this also have some characteristics, because if it's not powerful enough, you won't have a diagnostic image being produced, right? So it should sufficiently penetrate the patient and react with the film and the emulsion And in turn, it will produce a good contrast between the different shadows, right? It should be parallel or non-diverging to prevent magnification of the image. And 3, it is produced from a point source to reduce blurring of the edges of the image. And this phenomenon is known as penumbra effect, right? So when you're taking your X-ray image, the machine, unless it is made to move, right? It shouldn't be moving, right? The regular X-ray machine, the dental X-ray machine, I'm not talking about the panoramic and the cephalometric machines. No, this is the regular one. They should be in a stationary position, all right, when you're taking the X-ray. So the common types of dental radiographs that are used. So we have intraoral and extraoral. So the techniques that we use for the intraoral, obviously the film is placed inside of the mouth. So the different types we have are the periapical radiographs, the bite wing, and the occlusal, right? And for the X-ray, just to name two, we have the oblique lateral and the dental panoramic tomograph, right? So we'll be going through all the different types. There's more than two for the extraoral. I only listed two here, right? So we'll go through all of these techniques as we go along. So this is the end of the introductory presentation. Any questions?
No
You guys-
question.
Okay, no questions. All right. So I'll move on to the second presentation. All right, so radiation physics and equipment. So you guys would have done some amount of chemistry in high school, right? So we'll briefly just discuss the parts of the atom, which we look at in a few slides, right? So the X-rays, they're basically a form of high energy electromagnetic radiation and are a part of the electromagnetic spectrum, right? So X-rays are basically described as consisting of wave packets of energy, and each packet is called a photon and is equivalent to 1 quantum of energy. Now, the X-ray beam, as used in diagnostic radiology, is basically made up of millions of individual photons, right? So let's discuss the anatomic structure. So we know that, atoms are the basic building blocks of matter, right? They consist of minute particles, right? So let's talk about the nucleus. So what is in the nucleus, guys? Anybody, quickly.
Protons and neutrons.
And neutrons.
Good. So the protons are, does it have an electrical charge?
Yeah, they're positively
It's
charged.
positively charged.
Good. And the neutrons are,
Neutral.
as the name implies, neutral, right? So the number of protons inside the nucleus determines its
Atomic number.
good. You have the mass number or the atomic weight, right? Correct. Right? So the number of protons inside the nucleus equals the number of electrons, right? Which determines the atomic number. So let's talk about the electrons, and these are found where?
Around the nucleus.
Good. So they are found outside of the nucleus. They traverse on, they orbit around the nucleus and what?
Shells or orbitals.
Correct, right? So these shells, they are designated letters from K to Q, all right? And the orbits that are closer, or the electrons that are closer to the nucleus, all of these have binding energy, all right? And those that are closest to the nucleus, they have basically the greatest binding energy. So you need more energy to release those electrons from its shell, right? Everybody with me?
Yes, Doctor.
Yes? Good. So the binding energy is basically determined by the distance between the nucleus and the orbiting electron, and obviously it is different for each shell, right? It's just basically surface, right? In electron volts or kilo electron volt, all right? So 1 kilo electron volt is 1,000 electron volt, all right? So again, more energy is required to displace an electron in the K shell compared to that of the Q, all right? So the molecular structure, so we know that a molecule is basically comprised of 2 or more atoms joined by chemical bonds, or the smallest amount of substance that produces its characteristic properties. And it can be formed by 2 ways, either by the transfer of electrons or the sharing of electrons between the outermost shells of atoms, right? So we know what is ionization, right? So atoms can either exist in a neutral state or an electrical unbalanced state, which can be either positive or negative, depending on if it gains or loses an electron, all right? So ionization deals only with electrons and requires sufficient energy to overcome the electrostatic force that binds the electron to the nucleus. So radiation and radioactivity. And radioactivity is defined as the process by which certain unstable atoms or elements undergo spontaneous disintegration or decay to attain a more balanced nuclear state. Now, a substance is considered radioactive if it gives off energy in the form of particles or rays because of the disintegration of the anatomic nuclei. Now, in dentistry, X-radiation is used and not radioactivity. All right? So, ionizing radiation. Now, this is defined as radiation that is capable of producing ions by removing or adding an electron to an atom. So it can be classified into 2 groups. We have particulate radiation and electromagnetic radiation. Now, particulate radiation. Now, these are basically tiny particles of matter that possess mass, and they travel in straight lines and high speeds, right? So particulate, they travel in straight lines. On the other hand, electromagnetic, they travel in waves, which we look at in a few, right? So they transmit kinetic energy by means of their extremely fast-moving small masses, and there are 4 types that are recognized. So we have the first, where electrons can be classified as beta particles or cathode rays. In their origin only. So the beta particles are fast-moving electrons emitted from the nucleus of radioactive atoms. And then we have cathode rays, and these are streams of high-energy electrons that originate in the X-ray tube, all right? So the alpha particles are emitted from the nuclei of heavy metals and exist as 2 protons and neutrons without electrons. Then we have the third type, which are protons, are accelerated particles, specifically hydrogen nuclei, which with a mass of 1 and a charge of +1. And then we have neutrons, which are accelerated particles with a mass of 1 and no electrical charge. Then we have electromagnetic radiation. And this is defined as the propagation of wave-like energy without mass through space or matter. So the energy propagated is accompanied by oscillating electric and magnetic fields positioned at right angles to each other. And they could be either man-made or they occur naturally. Now, they also are classified as, they have two classifications, which are non-ionizing and ionizing. So only the high energy radiations are capable of ionization. Now, it is believed to move through space as both particles or waves. So the particle concept, it characterizes electromagnetic radiation as discrete bundles of energy called photons or quanta. And the photons bundles of energy with mass or weight that travel as waves at the speed of light. And move through space in a straight line, carrying energy of electromagnetic radiation. Now, for the wave concept, it characterizes electromagnetic radiation as waves and focuses on the properties of velocity, wavelength, and frequency as follows. So we know what velocity is, right? So it's the speed of basically the wave. We know what wavelength is, right? This is basically the distance between the crest of a wave and the crest of the next wave, right? So the wavelength, it determines the energy and the penetrating power of radiation. So the shorter the distance between the crests, the higher the energy and the ability to penetrate matter, right? And this is measured in nanometers for short waves and meters for long waves. Now, frequency refers to the number of wavelengths that pass through a given point in a certain amount of time. So frequency and wavelength, they are inversely related, right? If it's high, the wavelength will be short, all right? Everybody with me so far? Everybody understand? Any questions?
Yes, sir.
All right, great. So X radiation. Now this is a high energy ionizing electromagnetic radiation, and it can be defined as weightless bundles of energy without an electrical charge that travels in waves with a specific frequency at the speed of light, all right? So the X-ray photons interact with the materials, they penetrate and cause ionization. So let's look at the X-ray machine. So the X-rays are produced in the dental X-ray machine, and basically there are three study areas. We have the component parts, the X-ray tube, and the X-ray generating apparatus. So the component parts, it composes of three visible component parts. We have the control panel, the extension arm, and the tube head. Right, so we have the control panel here. We have the extension arm, which can also be seen in this older picture. And then we have the tube head, which is this area that is used to position the machine to the film, right? So let's look at the control panel. So the control panel, it has a on and off switch and the indicator light, right? So obviously you need to put the machine on in order to operate it, right? And the indicator light is illuminated when the equipment is turned on. So the exposure button, we also have the exposure button and the indicator light associated with that. So the exposure button, it activates the machine to produce the X-rays, all right? So this is where you hold the button and you firmly depress on it until the preset exposure time is completed. So, for example, if it is set at 0.1 seconds, so when that time elapses, even though you are still no further X-rays are produced, right? The sound, there's also an audible sound that is heard in addition to the indicator light, all right? So it does give an audible sound indicating that the exposure is also completed, all right? Sorry, excuse me. Now, control devices. So we're looking at time, kilovoltage, and the milliamperage selectors. And these basically regulates the X-ray beam, right? So the timer, this basically determines the length of the exposure time in seconds or impulses. Now the kilovoltage peak and the milliamperage, the MA, milliamperage, kVp, kilovoltage peak, all right? Now these selectors permit the dental radiographer to adjust and set the correct kilovoltage peak and milliamperes. Now most of the dental machines that are produced, they basically come with a preset programmable setting. So you don't have to be setting the kilovoltage peak and the milliamperage separately, right? Basically, it comes with, you can set the time, you can increase or decrease the time, and basically, according to the teeth or the tool that you're taking the radiograph of, you basically press that button for that specific tooth, right? So you don't need to do all of this anymore, right? Now, once you press those buttons, it automatically sets these factors into place because it is preset into that machine, all right? So the control panel is plugged into an electrical outlet and appears as a panel or a cabinet mounted on the wall outside of the dental operatory, right? So there are different types of machines too. You can have the wall-mounted ones as you've seen on the image that I've shown you earlier, and you can have the freestanding ones that stands on like a tripod. Those are also available, but the wall-mounted ones are the popular ones these days. The tripod ones, you know, they're there, but they're not as much as popular as the wall-mounted ones. The wall-mounted ones are very, very easy to use. You don't have to move it around. It's just there on the wall. You just move it to wherever you need to use it, right?
Doc, also they have the mobile X-ray machine.
Yes, yes, that one too. Very, very easy to use. It just take it wherever you want to go, right? Forgot everything about that. Thanks for the reminder, right? So the extension arm. So the extension arm of the machine, it suspends the X-ray tube head and houses the electrical wires that extends from the control panel to the tube head. So the extension arm, it basically allows for the movement and positioning of the tube head. Then we have the tube head, right? So this is a tightly sealed heavy metal housing that contains the tube head, the X-ray tube, sorry, that produces the dental X-rays. And there are component parts, and these includes the metal housing. So this is basically a metal body of the tube head that surrounds the X-ray tube and the transformers within it. And it is filled with oil that protects the X-ray tube and grounds the high voltage components, right? Then we have the insulating oil. So the oil basically surrounds the X-ray tube and the transformers inside the tube head. And this basically prevents overheating by absorbing the heat created by the production of rays, right? So the thing is, when the X-rays are produced, two things are produced basically, the X-rays and heat, right? So when heat is created, the insulating oil absorbs it. We also have a copper rod that also directs that heat away from that area, which we look at also, right? We have the tube head seal. So this is the aluminum or lead glass covering of the tube head. And this permits the exit of the X-rays from the tube head, right? So it seals the oil in the tube head and acts as a filter to the X-ray beam. Then we have the X-ray tube, and this is basically where the X-rays are generated. It is basically the heart of the X-ray machine. We have transformers, and this alters the voltage of the incoming electricity, all right? We have the aluminum disc, and they are basically 0.5 mm in thickness, and they're basically placed in the path of the X-ray beam, and they filter out the non-penetrating longer wavelength X-rays, right? So we have the lead collimator, and this basically is a hole that fits directly over the opening of the metal housing where the X-rays exit. So it basically restricts the size of the X-ray beam, right? Remember, when we're taking radiographs of our dental tissues, they're basically localized, right? It's not like the radiographs taken in medicine, where you're taking a larger area of the body, right? So the lead collimator, this restricts the size of the beam in dentistry, all right, or in this machine. Then we have the PID, or the position indicating device. So this is basically a open-ended lead-lined cylinder that extends from the opening of the metal housing of the tube head, and it aims and shapes the X-ray beam. It is also sometimes referred to as the cone. Right? So this picture basically identifies all the parts of the X-ray tube head that we talked about, right? So we have the metal housing, the insulating oil that directs the heat away. We have the X-ray tube where the X-rays are produced. All right. So we have the cathode, where when we plug in the machine into the electrical outlet, electricity is generated, right? Until we depress that exposure button, the electrons that are found here, they are basically diverted from this end, from the cathode to the anode, right? And this is the target tungsten here, right? This dark area, it's a filament here. And this is where the X-rays are produced, right? So when it is produced, they're all over, they're just bouncing all over in this area. As you can see also, this part of it, this is where the copper rod is, and this diverts the heat away from it into the insulating oil. All right. Now, this on the cathode, this area is called the meldonium cup, right? This is where you have the filaments with the electrons, all right? So we have the tube head seal. This ensures that the X-rays only passes through this area, right? Or it seals the oil, into place in the X-ray tube, right? We have the unleaded glass window, and this is where the X-rays exit. Now, even though a lot of X-rays are produced, only 1% of them actually exit the X-ray tube, All right. Everybody with me so far? Any questions? No?
No, Doc.
All right. So some of this I may have mentioned before, but we'll go along. So the X-ray tube again, it is the heart, as mentioned, of the X-ray machine. So it is critical to the production of the X-rays, right? So the X-ray tube is a glass vacuum tube from which all the air has been removed. So the X-ray tube used in dentistry measures approximately several inches long by 1 inch in diameter. Now the component parts of the X-ray tube includes leaded glass housing negative cathode and the positive anode. So the leaded glass housing, right? So this is a leaded glass vacuum tube that prevents X-rays from escaping in all directions, all right? However, as we've seen in the image before, there's that one on lead glass window that allows the exit of the X-rays when they are produced, all right? And this is directed towards the aluminum disc, which filters the longer non-penetrating X-rays, and it exits through the lead collimator into the PID, all right? So the cathode, it basically consists of a tungsten wire filament in a cup-shaped holder made of molybdenum. And the purpose is to supply electrons necessary to produce X-rays. So in the X-ray tube, the electrons produced in the negative cathode are accelerated towards the positive anode. And the cathode includes the following. It has the tungsten filament, which is a coiled wire made of tungsten, which produces electrons when heated. And then we have the molybdenum cup, which focuses the electrons into a narrow beam and directs the beam across the tube towards the tungsten target of the anode. Right? I just briefly explained this earlier. Then there's the anode. This is the positive electrode, and it contains a wafer thin tungsten plate embedded in a solid copper rod. Right? So the purpose is to convert these electrons into X-ray photons. So the anode includes a tungsten target, right, which serves as a converting electrons into X-ray photons, and it has the copper stem, right? And this functions to dissipate the heat away from the tungsten target, right? So this is another picture showing us the X-ray tube head, right? Everybody understand so far? Any questions? Come on, guys, you need to give me some feedback. At least one person.
No question, Doc.
Me, Doc.
Great, wonderful. So X-ray generating apparatus. So electricity and electrical currents, how do they play a part? So obviously we know that electricity is the energy that is used to make the X-rays, and electrical energy consists of a flow of electrons through a conductor, and this flow is known as the electrical current, right? So the current is termed DC, direct current, when the electron flows in one direction through the conductor. And another is the alternating current, AC, electrical current, when it flows in two opposite directions. Then there is rectification, and this is the conversion of AC to DC. So the dental X-ray tube, it acts as a self-rectifier in that it changes AC into DC while producing X-rays. So this ensures that the current is always flowing in the same direction, more specifically from the cathode to the anode. Remember, the cathode is where the electrons are, and the anode is where the tungsten filament is, where it converts those electrons into the X-ray photons, right? Or the X-rays. Then there's amperage, right? And this is the measurement of the number of electrons moving through a conductor. So current is measured in amperes or milliamperes, right? So we've looked at this before, which there were some controllers for this. However, there is none specifically for this anymore, all right? And then there is voltage. And voltage is the measurement of electrical force that causes electrons to move from a positive pole from a negative pole, to a positive pole. And voltage is measured in volts or kilovolts. Now, in the production of X-rays, both the amperage and the voltage, it can be adjusted. So in the X-ray tube, the amperage, or the number of electrons passing through the cathode filament, it can be increased or decreased by the milliamperage adjustment on the control panel of the X-ray machine, which regulates the temperature of the cathode filament. Now, remember I said that the machines long ago had this particular setting. However, the machines that are produced now, it is preset. All right, you won't see a direct controller for this this adjustment, this milliamperage adjustment. All right. Now the voltage of the X-ray tube current, or the tube passing from the cathode to the anode, it is controlled by the kilovoltage peak adjustment on the control panel. Now the circuits. So a circuit is a part of electrical current. Now, it is used, two electrical currents are used in the production of X-rays. We have the low voltage, or the filament, or the circuit, which is at the cathode, and then we have the high voltage circuit, right? So the filament circuit, it uses 3 to 5 volts, and this regulates the flow of the electrical current to the filament of the X-ray tube, and it is controlled by the milliampere setting. And the high voltage circuit uses 65,000 to 100,000 volts, which provides the high voltage required to accelerate electrons to generate the X-rays in the tube head, right? And this is controlled by the kilovoltage setting. Then there are the transformers, right? So there's 3 types of transformers. So we have the step down, the step up, and the auto transformer, right? Now, the step down transformer, it is 0 to 29 voltage to 3 to 5 volts used by the filament circuit, all right? So the step down transformer, it has more wire coils in the primary coil than in the secondary coil. Now, the high voltage circuit, right? That uses the step up, because remember, that requires 65,000 to 100,000 voltage, right? So this is where the step up comes into play. So it increases the voltage from the incoming 110 or 220 line to the 65,000 to 100,000 volts used by the high voltage circuit. So in this transformer, it has more wire coils in the secondary coil than in the primary coil. Then we have the auto transformer, which serves as a voltage compensator that corrects for minor fluctuations in the current. So the production of X-rays. So this is the step-by-step procedure, how exactly it happens. All right. So we plug in our X-ray machine. So electricity flows. All right. The machine turns on. So the electrical current enters the control panel through the cord. Right. So the current travels from the control panel to the tube head through the electrical wires in the extension arm. and the current is directed to the filament target and the step-down transformer in the tube head. Now, the transformer reduces the 110 or 220 entering the line voltage to 3 to 5 volts. Now, the filament circuit, which uses the 3 to 5 volts to hit the tungsten target in the cathode portion of the X-ray tube. Now, the thermionic emission occurs, and this is basically defined as the release of electrons from the tungsten filament when the electrical current passes through it and it hits the filament. All right. So the outer shell electrons of the tungsten atom, it acquires enough energy to move away from the filament surface, and an electrical cloud forms around that surface. This is around the cathode, right? Now, the electrons, it stays in an electron cloud until the high voltage circuit is activated. So this is basically activated when we press the exposure button. All right. So the electrons produced, they are accelerated across the X-ray tube to the anode, right? This is where the meldonium cup directs all these electrons to the tungsten target in the anode, right? So these electrons strike the tungsten target, and their energy of motion is converted to X-ray energy and heat. And we know what happens to the heat, right? It is directed through the copper stem, through the copper rod, into the insulating oil, right? Now, less than 1% of the energy is converted to X-rays, and the remaining energy is lost as heat. Now, the heat produced during the production of the X-rays is carried away, as I mentioned, and the X-rays produced, they are emitted from the target in all directions. They're just bouncing all over there, right? However, we have the leaded glass housing, which prevents the X-rays from escaping the X-ray tube, and a small number of X-rays are able to exit from the X-ray tube through the unleaded glass portion of the tube. So it travels through the unleaded glass window, the tube head seal, and the aluminum disc, and we know that the disc, it filters the longer wavelengths, right? Now, the next is the size of the beam, right? And we know that it is restricted by the lead collimator, right? So the X-ray beam, it travels down the lead line, PID, and exits the tube head at the opening of the PID, right? So that's how it is made and exits the X-ray machine. So let's look at the types of X-rays produced. We have two types. We have the general radiation or the break-in radiation and the characteristic radiation. So the term breaking refers to the sudden stopping of the high-speed electrons when it hit the tungsten target in the anode. So most X-rays are produced in this manner. Now, an electron rarely hits the nucleus of the tungsten atom. However, when it does, all of its kinetic energy is converted into high-energy X-ray photon. So instead of hitting the nucleus, most electrons just miss the nucleus of the tungsten atom, right? So when the electron comes close to the nucleus, it is attracted to the nucleus and it slows down. Consequently, an X-ray photon of lower energy results, and the electron that misses the nucleus continues to penetrate many atoms, producing lower energy X-rays before it imparts all of its kinetic energy. Now, as a result, general radiation consists of X-rays of many different energies and wavelengths. Everybody with me so far? You understand?
Yes, sir.
Then we have the characteristic radiation. And this is produced when a high-speed electron dislodges an inner shell electron from the tungsten atom, and it causes ionization of that atom, right? So once that electron is dislodged, the remaining orbiting electrons basically rearranges themselves to fill that vacancy. And this rearrangement produces a loss of energy that results in the production of an X-ray photon. So the X-rays produced is known as characteristic X-rays. And these accounts for a very small part of the X-rays produced in a dental X-ray machine. It occurs only at 70 kilovoltage peak and above because the binding energy of the K-shell is approximately 70 kilo electron voltage, right? So this is the amount of energy we need to remove that electron from that inner shell, all right? 70 kilo electron voltage. Now, let's look at some of the definitions we will encounter as we go along when we're talking about radiation in dentistry. So we have primary radiation, and this refers to the penetrating X-ray beam that is produced at the target of the anode and that exits the tube head. So this X-ray beam is often referred to as the primary beam or the useful beam. Then we have the secondary radiation that is created when the primary beam interacts with the secondary, when the primary beam interacts with matter. Then we have secondary radiation. It is less penetrating than the primary radiation. We also have scatter radiation, and this is a form of secondary radiation, and it is as a result of an X-ray that has been deflected from its path by the interaction with matter. So earlier, I'm not sure who asked the question if all of the X-rays are observed. No, some of it can be deflected, all right? So what happens is that it is deflected in all directions of the patient's tissues and travels to all parts of the patient's body and to all areas of the dental operatory, right? And this type of radiation, it can be detrimental to both the patient and the radiographer, right? So that's why we need to wear our lead aprons, and we have to stand behind that lead wall when we're taking radiographs, all right? So we need to be very careful and mindful of scatter radiation. Now, interaction of X-radiation. Now, what happens after an X-ray exits the tube head? So 3 events can occur. Now, the X-rays can pass through the pit. It can be completely absorbed or it can be scattered, right? So these are the 3 things that can occur when the X-rays exit that tube head. Now, at the anatomic level, there are 4 possibilities that can occur, right? We can have no interaction, absorption, or photoelectric effect. We can have Compton scatter, and we can have coherent scatter. So with no interaction, it passes through the patient, no harm is done, no atom is unchanged, no atom changes. There's basically everything remains the same, right? So the X-ray photons that passes through a patient without interaction, they are responsible for producing densities and make dental radiography possible. Then we have absorption. And this refers to the total transfer of energy from the X-ray photon to the atoms of matter through which the X-ray beam passes. So absorption, it depends on the energy of the X-ray beam and the composition of the absorbing matter of tissues, right? So at the atomic level, absorption occurs as a result of photoelectric effect. Now, in the photoelectric effect, ionization takes place. So the X-ray photon, it collides with a tightly bound inner shell electron and gives up all its energy to eject that electron from its orbit, all right? So the X-ray photon imparts all of its kinetic energy to the orbital electron, is absorbed, and ceases to exist. Now the electron in turn is termed the photoelectron, and then it has a negative charge. So it is readily absorbed by other atoms because it has very little penetrating power. So the atom that remains has a positive charge, and the photoelectric effect, it basically accounts for 30% of the interaction of matter with the dental X-ray beam. Then we have Compton scatter. Now, it is possible for an X-ray photon to be deflected from its path during its passage through matter, right? And at the anatomic level, it accounts for most of the scatter radiation, all right? Now, again, with this type of scatter, ionization takes place. So the X-ray photon, it collides with a loosely bound outer shell electron, not the inner shell one, an outer shell electron, and it gives a part of its energy to eject that electron from its orbit. So the X-ray photon, it loses the energy and continues in different directions, right? It scatters at a lower energy level. Now the new, weaker X-ray photon, it interacts with other atoms until all of its energy is gone. So the ejected electron is termed Compton electron or recoil electron and has a negative charge. So the remaining atom is positively charged, and this accounts for 62% of the scatter that occurs in diagnostic radiography. Then we have the last, which is coherent scatter, right? So this involves an X-ray photon that has its path altered by matter, right? So it occurs when a low energy X-ray photon interacts with an outer shell electron. Now, no change in the atom occurs, and an X-ray photon of scatter radiation is produced. Now, the X-ray photon is scattered in a different direction from that of the incident photon, with no loss of energy and no ionization occurs, right? So basically, the X-ray photon is there's just a change in direction without a change in energy, right? And this type of scatter accounts for 8% of the interaction of matter with the dental X-ray beam. So let's quickly look at radiation characteristics. So radiation characteristics includes the X-ray beam, quality, quantity, and intensity. So advances in dental radiographic equipment have produced control panels with predetermined settings for various anatomic areas of both the maxilla and the mandible. So the X-ray beam quality. So there are factors affecting the X-ray beam quality. We have the voltage and kilovoltage, the kilovoltage peak, density and kilovoltage peak. And the density is basically the overall darkness of the dental image, all right? So an increase in the kilovoltage peak results in a darker image. Then there's contrast and the kilovoltage. So contrast refers to how sharply dark and light areas are differentiated or separated on an image. These are used, which is 65 to 70 kilovoltage peak. A high contrast image will result. So an image with high contrast has many black areas and many white areas and few areas of green, right? So an image with low contrast has many shades of gray instead of black and white. Now, an image with low contrast is more useful than one that has high contrast, right? So this is able to detect periodontal or periapical diseases. All right? Everybody with me? Everybody understand that?
Yes, Doc.
Great. Now, expose time and kilovoltage peak. So the exposure time, it refers to the interval of time during which the X-rays are produced, and it is measured in impulses, right? So within 1 second, there are 60 impulses that occur, right? So for example, if we set our machine to take an image of tooth number 11, right? The impulses that may have been preset into that machine may have been one, like probably, let's say 10 impulses, right? That's 10 out of the 60 that is found within 1 second. All right. So again, these are measured in impulses. So the time required, it may take a very small time frame to take your X-ray, right? To take your radiograph, right? So it may take 0.5 seconds, 0.2 seconds, 0.3. It depends, all right, on the area that you're taking the image of, all right? So the kilovoltage peak rule. So when the kilovoltage peak is increased by 15, exposure time should be decreased by half. And when the kilovoltage peak is decreased by 15, exposure time should be doubled. But remember again, we don't have a specific setting these days to adjust the kilovoltage peak. All right? Now the X-ray intensity. Now the exposure time. Now, exposure time as a result, as with milliamperage, affects the number of X-rays produced. Now, a longer exposure time produces more X-rays. Now, an increase in exposure time produces a more intense X-ray beam. So the inverse square law. So the intensity of radiation is inversely proportional to the square of the distance from the source of radiation. So inversely proportional means that one variable increases. When one variable increases, the other decreases. So when the source to the distance receptor is increased, meaning if you increase the distance of the film to the tooth, right? The intensity, when you increase to the receptor, if you increase that, or you push it farther away, that means the intensity of the beam will be decreased. So that means that the image that will be produced, it may not be the quality that you require. All right, it wouldn't have the right contrast that you need to detect and make your diagnosis. Now, distance. So distance traveled by the X-ray beam affects the intensity of the beam. So the distance that must be considered includes the target surface distance. And this is basically the distance from the source of the X radiation to the patient's skin or their tissues. The target object distance, and this is the distance from the source of the radiation to the tooth. We have target receptor distance, and this is the distance from the source of the radiation to the receptor. So the distance between the source of the radiation and the receptor has a marked effect on the intensity of the X-ray beam. So as the X-ray travels from their point of origin or away from the target anode, they diverge like waves of light and spread out to cover a large area. So as the X-rays travel away from their source of origin, the intensity of the beam lessens. And that is the end of today's class. Any questions? Wow. Any questions?
Yeah, Doc, I have a question.
Mm-hmm.
Right. So in reference to the photoelectric effect, you said
Mm-hmm.
the,
Let's go back.
right. So the beam
Mm-hmm.
of electrons, right, targeted the inner shell.
Mm-hmm.
Thinking why not the outer shell of the material, the
All right.
outer electrons.
So they're establishing that 4 phenomena occur, right? Remember, this one targets the inner. The Compton, that targets the outer. If you notice, right?
Oh,
Yes. So that's why we have the differentiations with all of these. So 4 things happen when X-rays are produced and they hit matter. So these are the 4 that occurs. The inner shell, the inner electron can be ejected. Some target the outer electrons, right? Some just have a change in direction, right? And some don't have any interaction at all, right? That's what basically happens,
clear now.
right? Any other question? Sorry about that. Any other questions?
Nothing like that.
All right, great. So again, your first quiz will be next 2 weeks. It will cover the topics that we have looked at so far. According to your course outline, your first test should be within week 4. So just keep an eye out for that. I'll set probably the date for either Tuesday or the Thursday. It depends on you guys, whichever day you guys prefer, we will do the test on that preferred date. All right. Now, as after the test, I think we'll have a class just to continue and finish these presentations. All right. So if you guys don't have any questions, I guess
Well,
yes.
The quiz or the test will be by or
in person on ExamSoft. Yes.
So in that case, we'll probably mostly appreciate if at all the test can be on I guess Tuesday.
Okay.
Because,
Tuesday.
on Tuesday and Wednesday we have in-person class with Dr. Ali. The rest of the days we normally get Zoom most of the times for now.
Okay, well fine. Tuesday can work. Yes. Well, Wednesday I don't have you guys, so yes.
Yes,
So Tuesday, we set Tuesday. Let me see. What date is that? 3, that's the 20th. All right. No, sorry, the 19th. The 19th of September. All right. So guys, please study. I love to see high marks, high grades is. Yes. Don't like to be disappointed. So yes, please study. I assure you it's not easy, but if you study, you will pass. All right. So that is it for now. See you guys this afternoon. Have a good one, guys. Goodbye.
No.